All right. Hello and welcome to another episode of the Measurement Lab. I'm Elijah Carey, and today I am joined by Greg McKaskle from LabVIEW R&D. Greg, let's start by telling everybody how long have you been with the company and what was the first version of LabVIEW that you worked on?
I joined the company in May of 1990, and I did a little bit of work on LabVIEW 206 or 21, something like that. But the primary thing I was hired on to do was support LabVIEW to other platforms.
At the time, it would have been porting it to which platforms?
It actually was porting it to SCO Unix, which was never released. That later turned into the Windows 3 and the Solaris editions of LabVIEW.
Okay, and remind me, the first version of LabVIEW for Windows was what release?
2.5.
2.5. So you would have worked on that then as part of that.
I did.
That did work. Awesome.
That was in 1992.
Okay, so you've seen a lot. And actually, if you could, we have a few topics keyed up for today, but what are some of the more exciting features of technologies you've had to work on throughout your career with regards to LabVIEW?
Starting with the company, I worked on the visualization, the controls, the UI, whatever you want to call it. That involved, data displays, user interaction, data entry kind of controls. So my initial foray, I guess, was the graphs and the charts. So, there's a lot of modernization stuff that we had to do. Even at that point, they already existed. They were written for Mac only, and we had to make them multi-platform and, make them a lot more capable of, higher rates and things like that. I've worked on most of the controls at some point, managed people who worked on the controls. And by that, I mean, sliders and knobs and buttons and charts and graphs and tables and whatnot. Let's see. I guess one other kind of cool things we did in the later 90s is we did the subpanel control, which let us put panels inside of panels. And that was a capability that really opened up the ability for us to allow code to be more modular and allow for us to make editors inside LabVIEW. So I made extensive use of that at some point. Yeah.
Well, and this is why we picked you today to come and talk a little bit about how LabVIEW's user interface works, specifically the user interface that we build on the front panel. I know when I talk about LabVIEW and when asked, what are the core capabilities, I've got my list. Amongst those items is the user interface and how uniquely well suited it is to display and interact with data, specifically data that engineers and scientists care about. So I want to get into a little bit about how it works and some of the unique capabilities, but maybe start by helping us understand some of the requirements that were especially unique as a result of the application areas we served. That, I'm assuming that there were constraints and requirements that were uniquely necessary for engineering scientific applications. Could you just talk a little bit about, especially in the early days, what those were and how those compared to other application areas and the capabilities of other tools at the time?
Sure. In the early days, the PCs were pretty limited in what they could do. They might have an accelerator card. Most of them weren't even true color. So we were often dealing with like 8-bit or 16-bit color. The Macs.
You're talking about a graphics card, right?
A graphics card.
Okay.
They were a little more. The Macs were a little more capable, but the other machines were pretty limited. But the goal in a lot of cases was to try to replicate what you could get on a very high-end instrument using only a PC. So in other words, you wanted a scope, or you wanted a digitizer, display, or something similar, or a chart recorder, but you didn't want to spend, $5,000, $10,000, $20,000. You wanted a similar capability with a PC. One of the early things we tried to do, it was kind of interesting, was we tried to make a DPO scope, those digital, the decaying phosphor oscilloscope displays that would do either false coloring or they would do like persistence. So that was kind of an interesting project that it never actually made it into a control, but we were working on, how you would do that sort of with the video card capabilities you had available. The instruments at that time used a lot of video memory and special processing to do it, and we were trying to do it on a regular PC.
I always kind of assumed, like in a scope, especially when they used the tubes, like literally old school scopes, that brightness decay as the traces got older was just a byproduct of the technology and maybe not even intentional. Was it actually an intentional design or something that was just a remnant of that technology that people liked and ultimately wanted in modern solutions?
Right. No, that was actually kind of a side effect. Once you
Yeah.
excited the phosphors, it takes a while for them to emit all of that energy as light. And so but like, as you say, that gives your eye enough time to perceive the shape of the trace. And if it goes on for too long, you get a blurry, muddy mess. And so the amount of energy you try to put into the display, that was the ability that they were balancing this and doing this in analog form, chemically. And we were, though, oftentimes trying to replicate stuff like that, digitally, mathematically. So
Yeah.
yeah,
I guess it would have given you a nice simple way to say, hey, it's something significantly different in this period than the last one. But I guess that dates it. I mean, to think that you were looking at, I guess, CRT based displays or tube based displays and using that to devise software based representations of data in LabVIEW. I mean, that kind of gives you a sense of how nascent technology was relative to what we were aspiring to do in LabVIEW. So ultimately, then I think there's two things that come to mind around the nature of UI controls that I find interesting. One of which is the fact that obviously we've really catered to engineering and scientific data. But then two, the fact that when I design a user interface on any given platform, it looks the same across the others. And that's not necessarily something that's as easy in other tools. What did we have to do differently to enable LabVIEW to handle large amounts of engineering scientific data? How is it different from the data that you would typically want to display and interact with? Call it general application software.
I think what you're getting at is, it's not uncommon for us to have a buffer that is, coming back from an instrument that's quite large, and we need to process it rapidly. So I guess it's really not all that different from what video games and other visualization software does, but we basically try to keep it as efficient as possible. And we have algorithms we run over it. Like, I guess one of the early things I did in LabVIEW was I implemented decimation algorithms for the graphs and charts, so that when you had, millions of points of data that you wanted to chart on the screen, we do minimal processing on it, and then we identify the points that are of interest, like sort of the high points, and then that's what we used to do the display. So
just to be clear, if I send 1 million data points to a graph, it doesn't actually display all 1 million of them, right?
There aren't that many pixels. It's not possible. So what it does is it tries to identify the ones that it can cheat on, and you can't tell the difference. So effectively, the envelope of the waveform is what it tries to represent.
And that's all about performance, right?
Right. And that allows us to do less processing. So the bottleneck in a lot of those cases is when we hand that data over to the operating system, ideally, we just hand them 1 million points and say, draw this. But we found those libraries would choke. So it was our job to, winnow it down to the ones that mattered and send that to them. So we do that for a lot of our displays. So if you send a lot of data to tables, they only figure out but what are they going to see? The rest of it, we don't have to process so much. But you may have to do some minimal processing to get the scroll bar right or about right. And so it's, it's literally looking for optimizations. It's what we do in our drivers. It's what we do in our hardware. A lot of things.
Yeah. I didn't realize that. I knew we did the decimation of graphs and data display. You're saying that we also do that for things like tables and charts? Okay, that makes sense. So what's going on under the hood? Like, peel back the layers for us a little bit. When I define a front panel in LabVIEW, what is it doing to determine how that gets rendered, and especially when I move from one platform to the other? Can you give us give us a little understanding of the technology?
Due to when we made our displays, we found ourselves needing to implement a lot of this ourselves. X Windows had controls, probably the nicest ones out there, but they really weren't portable, and they really weren't that capable. Apple had controls. They weren't scientific in nature either. And Windows controls were really primitive. Most of those were 16 colors, not 16 million colors, 16 colors. So effectively, we designed our own controls, again, not unlike what a video game or maybe some other more advanced, editing package would do. And as we did that, we made abstractions that let us take those to kind of make them independent of the platform we were running on. So for example, on X Windows, on your Linux platform these days, we don't really use the high-end controls. We use basic primitive elements, events, and we draw things pretty low level. And that gives us a lot of performance and a lot of flexibility to do what we want. We obviously take advantage in certain cases of scroll bars are an interesting example of where every platform decides somehow the scroll bars are like the chrome on the car. You have to make them look like the OS. And so that's an example of where we have to sort of plumb things into them to say, yeah, draw your scroll bar here. But it's a lot of times it's really just the pixels. We don't actually even allocate their scroll bar objects and do all those things. We have our own abstractions. So,
So it sounds like we've always had to strike a balance between the things that we have to do and then leveraging the things that
and
people
actually, I think one of the things that's kind of interesting is our ability. We long ago decided to try to make a system set platform controls so that we could make our own dialogues. We'd sort of fool ourselves and fool other people into thinking that we were a native application. And what that allowed was for LabVIEW panels to look more or less like the operating system. In hindsight, I wish we had gone a little further on that and done controls that normally don't show up in dialogues, things like graphs and additional things. Our goal was to do the save dialogue and the print dialogue and so on. And we did a pretty good job. And it's crazy how little we've had to do going all the way through Windows NT, Windows Vista. I mean, those things look crazy, right? Do you remember what just even looked like? Into Windows 7, Windows 8, now 10 and 11. We've had very little effort. We had to touch on those controls to just follow them all the way through. And the same thing for Apple. The appearance and interaction of those controls is actually pretty realistic, pretty true to the platform, but it's our own implementation. But we leverage parts that give us.
Same
so
for
Linux
Linux,
is
I
interesting
assume?
because they
Same for Linux.
early on they had all these window managers and desktop managers, and it was harder to leverage that code. So there we unfortunately we kind of look like an old Windows platform or something like that. It would be cool to hook that up, but we haven't looked at it in a while.
Okay. So how would you compare the capabilities we have? I mean, obviously there's a lot of languages out there like Python, Rust, C, and if you were to survey the landscape of tools out there specifically for engineering scientific data, any thoughts on how you would compare our
from a language
capabilities
standpoint
versus
or
whatever
UI?
else might be out there? From a UI, like if I want to display large amounts of waveform data, engineering data, just curious how we stack up, in your opinion, as somebody who's worked on the UI and probably looked at standard solutions for other languages. Just interested for your off the cuff take and how you would compare our approach to what's
the reason
out
I
there
asked,
for other languages.
to clarify, is that most of those languages don't even have any sense of displaying data. It's a print statement, or it's very primitive. You immediately have to go find a library to hook into. So these days there are actually some good libraries out there, but this is where you would go get Plotly, or you would go get some dashboards in a browser or whatever as your back end. One of the interesting things that happened at NI back in the day is we actually had Lab Windows, CBI as well. And that was actually more the traditional, so like now you had C programmers using a graph. And so that actually gave us a compare and kind of kept the race going, so we could figure out who was faster and, try to beat each other. But our data management, while it is abstracted, is pretty efficient. We do make extra data copies and things like that, getting to controls and indicators, but I would say we stack up pretty well, and especially with the ease of building that interface. So, and okay. I was going to say, and starting
I know for some
LabVIEW 5,
sorry, finish it up.
we decoupled UI from the diagram execution, which is actually, again, not an easy thing for people to do if you're writing your own program. And that allowed the diagram to run much faster than the UI, and sort of handles that, magic buffer management stuff that is somewhat hard. So that means your diagram can be, working almost unburdened, and the display is doing its best to keep up, showing you the data that's you're capable of viewing on this hardware.
Well, so let me double click on that, because we have another episode with Akash where he explained some of the under the hood plumbing with regards to how we handle threads and multi-threading in particular. And I know 5.0 is kind of a seminal moment for us where we really leaned into multi-threading even before the dominance of multi-core processors. And I was going to ask you to explain how we handle the UI updates and UI processing from a thread perspective. Was 5.0, was that also the point at which we first put the UI in an independent
up until then,
thread?
We took turns. So the diagram would execute for a while. They would ask the UI to do something like a display, and the UI would do that display, and then it would go back to the diagram and execute for a while, go talk to DAC or do some processing or analysis, and then come back to the UI. And in 5.0, we were able, if your operating system and hardware supported it, we're able to have threads that did execution and then the thread that did the display. And they minimally talk to each other. And so the diagram drops off buffers periodically and says, here's the latest. And the UI will, as it's able to, it'll pick those up and render those for the user to see and interact with. Yep.
Okay. So I know from a code execution standpoint, obviously we have some customer applications that have, dozens, maybe even more in terms of threads or independent parallel processes, especially if you get into like dynamically launching actors, et cetera. When it comes to UIs, I think most people start with a fairly rudimentary like graph, buttons, knobs, right? That's the average starting point for most LabVIEW programmers. But there are plenty of very large applications out there with especially complex user interfaces. I'm thinking of one in particular in the space industry, but there's many others. And what happens from a memory, performance, and threading perspective when you get into these applications where you have, multiple panels popping up? Maybe you're using a bunch of different sub panels and thousands of different data displays. Is that all happening in a single UI thread, or do we actually spread that out across multiple threads?
At this point, we still have one UI thread, and that is used for user interface as well as other serialization things. So when you save a VI or load a VI or compile a VI, the UI thread gets used, it gets reused. It would be very interesting to be able to spawn that off and split that out. But early on, the operating systems and display systems really were capable of, in fact, even today, there's a lot of things you can't do in Windows with multiple threads in UI. You have to be very careful. So, we had early on in LabVIEW 5, we had released LabVIEW 5, but we hadn't done 6 or maybe 5.1. And somebody from Bell Helicopter, I think it was, showed up, and they had a Hewlett-Packard workstation, and they had 300 panels all displayed on one monitor, and they were all independently updating. And that was very interesting. Found some remaining bugs that we had shipped in 5.0. It was, in those days, it wasn't, periodically we'd have customers show up with their app and we'd help them debug it, and they'd find our bugs and we'd find theirs. And anyway, that was an interesting system because even before we had sub panels, they were simply tiling windows across, building lots of little, little things on the display, and they had 300 panels updating independently, different at their own rates. So 300 VIs that were all open and running simultaneously. So, and again, the number of threads there probably was only, 10 or 12 or something like that. Like you say, it's possible that there's a lot more, but at some point, the hardware doesn't really get a lot of benefits out of, 100 threads these days. we are totally capable of doing that, and we occasionally will do that for test cases. But to answer your original question, yeah, we have a single UI thread because we just try to minimize what we do in that UI thread. I would love for us to continue breaking things out and not interrupting displays. But it turns out that it works pretty well to,
Yeah. I mean, I think the point there is we have a single UI thread, but I am aware of many customers like the one you described, where you just have all these different dynamic displays and they're incredibly performant, showing vast amounts of data, sometimes over like dozens of different screens for a single station. So I think that speaks to
some
the
of that is also
performance and the
true because
capability.
we try to be sort of careful about how we redraw controls. It would be very easy to just redraw the entire window anytime anything changed. We try pretty hard not to do that. We try to do minimal drawing. So the algorithms that we've done, over the years, like when we get new data, like with a decimation, we try to draw the minimal amount. So if you're on a slider and the value is changing slightly, it may not even redraw anything, or it may redraw only a tiny bit of the slider. But we know what's expensive, but we try to avoid the expensive things so that our displays are fast, even though we only have one thread.
So let me ask you something. I remember that there was a customer who had just an absurd number of different data displays. And I think this was, I don't want to get the version incorrect, but we added a feature to LabVIEW that basically allowed a UI to be updated based on, I think, a DVR reference. You know what I'm talking about? Can you comment on what that does and how that helped increase the performance of this especially massive UI? I think it's something that many people watching may not be aware of. I think we probably also want to caveat, it's almost certainly not necessary for 99% of users, but for that 1%, what does it do? How does it work?
So I don't exactly know what you're getting at. Let me switch topics to one of the thoughts I had when recently when talking to some customers was letting people wire DVRs up to graphs. Right now the graph takes in the actual data, and it actually copies over that data and stashes it so that the diagram can go on and do other things. And the iMac display forever has done this by reference. The iMac Vision display, we don't actually copy the data.
Hey, so Greg, so we'll edit this out since you didn't know the answer. I was referring to the work we did for SpaceX.
Gotcha. Yeah. Well, to answer off the cuff, what we're doing there is a lot of that had to do with Rob's work with parameter passing through the VI server. I don't think it was actually display stuff. They're using control IDs.
Well, no, we did have a way to update controls.
So yeah, do you want me to give the answer to that now? Because it doesn't have a lot to do with displays, but it was a very nice performance enhancement.
Okay, so yes, I'll ask a question more briefly, and then you can explain, hey, that doesn't have to do with displays, but here's how it is relevant, okay? All right, so Sean, sorry, you'll have to cut this back in. Okay, let me rewind. So, Greg, I know that there was a feature we introduced a few versions ago in LabVIEW for a very specific customer that was aimed, I believe, at accelerating the update rate of their user interface because they had just such massively complicated displays. Can you explain that technology, when it may or may not be appropriate for somebody to use?
That feature was added for the customer had very loose coupling in how they were updating their displays, and they were not using terminals. They were using the VI server to update their displays. And the traditional way of doing that was involve name lookups and some things that would happen, sort of late in the game. So you'd say, I have a control named this. Yeah, and here's a new value.
Were they using reference wires? Terminal?
What we put in was the ability to look up those names early and stash the indices. So later, if you were willing to use the set by index, you could actually get much higher performance. I think 50 to 100x performance on simple data types. So it was very effective.
And if I wanted to use that
Um,
feature, how would I go about finding that in the palettes?
there's
What is it called?
set control value by index or something similar to that in the VI server. And then there's a way to look up with the name so that you will know those
Okay.
indices, other things you're going to update later. So it just lets you preload a bunch of control. They're not references, but essentially they are like references, and say, these are the ones I'm going to be updating. And then inside your loop, you're not doing name lookups.
Okay. So who actually needs that? I think this is one of only a handful of customers that are actually using it at scale, because otherwise it's not necessary. So safe to assume that the average user probably not going to see a meaningful
I
difference in
mentor the
performance. Any
robotics
guidance on
team
when
at
it
the high
should
school, and
actually be
we
considered?
actually used it to enhance the performance even on RT, because we were dynamically invoking what we call commands. They're sub VIs.
Oh,
And we wanted to, we basically want to get it done quicker. And we had a couple extra milliseconds that were being added on these dynamic calls to pass in these parameters. And so we used it there and cut the time down appreciably. But it's anytime you,
sure. Oh, so it was to
it was
read values
passing data.
on the, or was it display values, or both?
We were literally pumping data into VIs and pushing the run button. That's how these had to work. They were loosely typed.
That's a.
It's really about
So
putting
this
data
really have to
into
do with the UI in
controls
this
on
case,
another
just
panel
about performance
using
of
VI server.
communication.
But it's a neat trick, but it's not used. It's not needed very often if you use the more type safe mechanisms like terminals, or even the call by ref. You don't really need this if you use those mechanisms. So this is for those.
Okay. By the way, it also highlights something that, the unusual reality that the user interface in LabVIEW is also the right. I'm thinking of the analogy, like the header function for a function call, right? It's like how you pass values into and out of a subroutine. I mean, was that a deliberate decision that was made at some point in the early days, or is that just kind of
The
naturally how
fact
it
that
evolved?
a VI is a function has always been there. And I even back in 1990, it was sort of a little surprise of like, really, we're going to do displays this way? And I think Jeff Kodosky and others were like, well, it's worked so far. Let's keep going. And when we added, first they were called attribute nodes, later called property nodes, and the VI server, and also locals and events, it became way more powerful. And in most architectures, you'll see that like user interfaces aren't really just sub VIs. They're they're a special kind of a VI. They're not really just called willy-nilly. So you end up with sort of functional sub VIs and pretty display sub VIs. So under the hood, they're the same thing. But you generally, you often do break them up a little bit. So you'll end up with a thinner UI skin on top of the functional stuff. But you don't have to do it that way.
Well, and I know that, sure, but I know when talking about the advantages of LabVIEW, there's the ability to display all this data, the performance of it, et cetera. I also am often I often highlight the debugging tools among them. It's often forgotten the fact that every single function has a standalone user interface. Right? How unusual is that? And often incredibly useful to understand like what's happening.
I was working with this goes back to about 2008 or 9, and I was working with another woman from the company name doesn't matter. Anyway, we were doing the same application, sitting next to each other at the desk, and we were doing example code for the first robotics competition. And so we had a webcam, and we're doing some processing on the data. And I was nearly finished, and I started noticing she was struggling, and I started helping her a bit. And she was writing it in C, and I was writing it in LabVIEW. And because I was able to just open up a sub-VI and see the images flowing in and out and see the results flowing in and out of this processing VIs, I was able pretty quickly to point out to her that like, yeah, you're holding your camera way too close to the thing. And you need to hold it back. See? And I could point to the picture, and she could see what was. And then, anyway, she was trying to do with print statements, and the ability to see your data. Um, it's it's something it's hard to put a price tag on. And you don't always
Yeah.
need it, and you can't always see all your data. Obviously, computers are very capable, but at key points, being able to see your data and understand it and go, oh, I crossed the wires, my cable fell out, the camera's not focused, whatever. I mean, those are like those moments where you save yourself who knows how much time. So this is where data visualization is a little bit of the secret sauce that LabVIEW, Lab Windows, and products like that brought to the table. Because otherwise, you're sitting there with a print statement.
Yeah. I have to say, you can't display data when you're talking to a piece of code written in C. It's a lot of extra work to then come up with something that actually is not just capable of displaying the data, but does so in a meaningful way. And so it's overwhelmingly not the case that people do that. I agree. Anyway, I'll get off my soapbox. Awesome insights. One last question for you. I'm sure you've seen a lot of user interfaces from our customers throughout your career. Any in particular that you thought were especially cool or especially impressive that you're able to highlight?
I remember seeing some of the ground control UIs from SpaceX. I didn't see them in action, but I saw mock-ups, and I was very impressed with how much data and all of the different information that they intend to display. It was very well thought out. The people who worked on that, had a very tough job. So that was impressive. Maybe answering a slightly different question, though, I guess one of the fun games I like to play is as I watch television shows or, news programs, like looking for LabVIEW displays. It's kind of a fun little game. I saw one just the other day where people were testing drill bits in Massachusetts. Somebody was taking a tour of a factory that has made drill bits for 100 years. And they go into this room and they have this enormous screen, and they're talking about their modern system for determining, how well their drill bits are working. And it's like a LabVIEW panel, and they've got all these graphs. They'll just do this repeated stuff, and they present the data in a way that they can observe patterns. But I've seen some really cool ones for semiconductor wafer failure identification. That's another one of those where there's still a lot of cases where humans identify the pattern. If you put the data in geographically on the wafer, you can identify all kinds of cool things. So that was pretty cool, like a heat map of failures on semiconductor wafers. That was pretty cool.
I know I've done the same thing, and oftentimes, like, the good and bad of LabVIEW is like the unrefined user interfaces are very easy to spot. However, I think it's also worth pointing out that I also work with a lot of customers who've gone who have made LabVIEW look like any other piece of application software. Right. And I think that's something some people, especially people new to LabVIEW, don't realize is entirely possible, inclusive of like resizable, responsive user interfaces, as you would expect with any other piece of application software. So I'll highlight a lot of examples, but obviously a very public one is a lot of the software published by our friends at JKI. It's all written in LabVIEW, VIPM in particular, all very resizable and responsive. But there are many more examples just like that. Of course, the downside is they can be harder to spot because they look like any other piece of software. But the graph, the classic LabVIEW graph with the gradient left gray side, people tend to use that because it's one of the default things that come up, and when you see it, you instantly know it's LabVIEW. So I actually kind of love that. Even though for my application, I would quickly customize that to look a little bit more modern. But anyway, Greg, I want to thank you. And I know you've worked on a lot of other things besides user interfaces, so we're likely to have you back. But as always, thank you for watching. If you have any questions or follow-up for Greg and want to tap into his expertise about user interfaces, please do leave a question in the comments below. And otherwise, subscribe to see this and future episodes of the Measurement Lab.